So, good evening, everyone. Today I'll talk about neural program synthesis. It is a contemporary approach for solving a program learning problem, which consists of automatically generating a computer program consistent with some specification. Firstly, I will introduce the program learning field with some examples, and we'll try to give a motivation about why it could be useful in practice and what potential benefits could we achieve if we try to combine program learning algorithms with a neural network approach. First, the main part of my speech will consist into two subparts. First will be about programming by example. It's one of the most common type of instances of program learning problems. Here, the specification of a problem is of a program is just a few number of input and output examples of the algorithm's evaluation. In this type of task, we'll observe briefly two algorithms, Flashfield and RobustField, that are designed for string editing for string editing domain. Flashfield is an example of a classical algorithm, and RobustField is an example of algorithm that uses a neural approach. In this part of speech, I will try to give an intuition about what potential features we could achieve if we try to use neural networks for solving program learning tasks. And the second part of the speech will be about the opposite direction of this combination. It's about using a program learning module as a part of neural architecture. This will be observed in application for visual question answering problems. I'll observe two recent models, Neural Symbolic VQA and Neural Symbolic Concept Learner. So as for motivation, it's quite natural and general. So human beings are capable of extracting regularities even from a small amount of information, while contemporary neural networks tend to require more and more data the more powerful algorithm they present. And in this case, program learning instances are actually are an example of where this capability of extracting regularities from a small amount of information plays a critical role, because we usually have a specification provided by user, and a typical user cannot provide the algorithm with a lot of input-output examples or a different type of specification. So it could be seen potentially as an AI benchmark in the future. And the second motivation is that combining it with neural models can get us some potential benefits. So going into examples, the first one is really common for all of us. It's an example like in Microsoft Excel spreadsheets, where we have a few number of input-output strings, and we like to perform the same transformation for a large set. It can be large for a set of input strings for which the output string isn't provided. The more exotic example is about graphics generation. This particular image was taken from the paper about generating programs for image generation in TIC's LaTeX module. So the only thing we need to do is to draw an image and to put it as an input of an algorithm, and we'll get the program that that tries to approximate this image.
Could you please return to the previous slide?
Yes.
I didn't quite understand what was the algorithm for converting input stream to output stream.
I believe it's like
screens, right? In the output stream.
Sorry, I didn't hear.
There are errors in output stream. Was it done?
Yeah. It's this particular image was taken from the RobustField paper about applying neural models for solving this type of task, and they put it noisy characters for evaluation, just to measure the robustness to noise of the algorithm.
We'll talk about this later.
Yeah.
Okay.
And there are many more examples of applying program learning program learning instances. For example, at the left, we can see the picture that's about the Caro programming language. That is, I believe, frequently used as a tutorial programming language for school students. And we aim to generate a program that will move the robot from the point A to point B, point A to point B, through some different obstacles. And the picture at the right is about visual question answering that we'll talk at the second part of the speech. So the first part is about program learning as a main task that we try to solve. So when we try to design an algorithm that will solve a program learning instance, first two things we deal with is firstly how to provide a specification of the program, because providing a definition that will lead to a single program is pretty difficult in theory and is intractable in practice. So practically, I could imagine just two ways of defining a single program. First is to give all possible pairs of all possible inputs and give all possible outputs corresponding to the inputs. And second will be in typing a program that we aim to do. The solution of this problem is quite natural. We just do not need a full description. We just need an approximate one, and it is defined by input-output examples. The second problem is that we actually need a programming language to derive the programs. The main approach for solving this problem is to design a so-called domain-specific language. It's just a simple language that is usually defined as a, for example, context-free grammar. But there are many different types of these languages. But grammar type are really we can see grammar types really often. The benefits that this approach could give to us is that the domain-specific language designed especially for a task can contain some structural information about the data that we aim to process. Here are the simple definitions about programming by example setting. So we have xk and yk is a set of so-called observed input-output examples. Xk test is the set of test or assessment examples. We aim to output the yk test for corresponding assessment inputs such that they will be as close to the ground truth as possible. As we will see in the neural approach, we can have the situation when we derive the program explicitly, or it could be contained in an algorithm in implicit form. So, but when we derive the program explicitly, we set assessment outputs as the result of evaluation of our program at our assessment inputs. And we require the consistency with observed input-output examples. In neural program learning, these instances are, it's usually modeled as a sequence-to-sequence task. And there are two main approaches. First is a neural program induction, when we generate an input or an output directly from an input, and the program here contains an algorithm in a latent representation defined by the middle layers of our neural network. And the second one is neural program synthesis, when we derive the program explicitly.
I understand right that one of the motivations is to obtain interpretable algorithm.
Excuse me?
Interpretable algorithm.
Yeah. And talking about the comparison of these two approaches, neural program synthesis is obviously more interpretable than the first one, because the first one is just directly solving this sector-sec task, and we just make the we just make the operation with hidden embedding activations and so on. And here we can just execute a program and see what type of operations neural network wants to perform, something like this. And we will see by applying the robust field model that synthesis achieves more comparable, competitive results. Yeah, and while explicitly generating a program, there is a question how to, what is our vocabulary. But having a simple programming language, we just have a list of possible operators that could be converted into tokens. So it's not a problem because the vocabulary is defined by our programming language, by our DSL. So Flashfield. Flashfield is a legendary algorithm that is used in Microsoft Excel for string editing, and it is a so-called rule-based algorithm. It's an example. It's a great example of a classical approach where this algorithm works invisibly fast, even if we process a large amount of strings, and it achieves really good quality, even conditioning on a small number of input and output examples. And this was made possible by designing a really expressive DSL with a lot of with a high number, with a lot of different with a lot of sophisticated operators such as loops, cycles, and so on. And applying different smart search techniques and cutting the paths of search over the space of possible programs, like in discrete optimization tasks. But there are two main drawbacks in this type of approach is that, as we will see, this approach is fragile to noise, for example, typos in our observed examples. And this requires a lot of engineering while being a task that is similar to a machine learning task, where we have inputs with outputs, and we want to predict outputs to new inputs. So this motivates us to try a neural approach, and one of the competitive models in this setting is called robust field, and it uses neural program learning approach, and actually authors compare two different techniques, namely neural program induction and neural program synthesis that I was talking about. The authors of this paper also designed their new domain-specific language that was actually much simpler than the Flashfield's one. They use a multi-attentional architecture of the sequence-to-sequence type of networks. Well, multi means that while decoding a program, we attend on both input hidden representations and output hidden representations. Going back into programming by example setting, we do not have actually ground truth programs. So there are two possible ways to solve this problem. First would be, and is actually applied in this model, is synthetically generating programs from our domain-specific language for learning. So we just generate an input, generate a program, evaluate the program on the input, and get the output. We don't even need an output. We just need an input to a program type of ground truth. The second approach would be to use reinforced gradient estimator or some techniques like this, because what we need actually is to sample a program from our neural net and to get a report and to get a gradient update. And it turned out that with this type of architecture, our model achieves comparable with the Flashfield and even better results. And let's take a look at them.
I have a question. So
yeah.
For induction approach, do we still generate the program in the domain-specific language?
No, we do not have a domain-specific language. We do not explicitly generate a program. It's like we call it so what can be said about the program that we have a latent representation somewhere in the middle of our neural architecture. Okay, in these two tables, in these two graphs, first thing that we observe is the comparison of induction and synthesis robust field modules that are actually nearly the same, but in the induction approach we just generate output strings, and in synthesis approach we generate programs in our domain-specific language. It can be easily seen that synthesis approach with sufficiently large beam size outperforms induction approach by 20 to 30% of accuracy, which is pretty high, and which I believe proves that providing an algorithm with some prior structural knowledge could be really useful for for an overall quality of an algorithm. And the second table shows that demonstrates the comparison between performing on a noisy data of robust field algorithm and Flashfield algorithm. And it can be easily seen that on the clean data, our algorithm achieves comparable quality on comparable quality on the so-called Flashfield test dataset, which I forgot to say that Flashfield test dataset contains input-output examples from the real-world spreadsheets, not synthetically generated. We achieve comparable performance with Flashfield on clean data, and our derived algorithm is much more robust to noise when we have when we have one or more typo in each observed example. Okay. Yeah.
I have a question. Can we theoretically, in the decoding stage, generate a program that is syntactically not correct?
Yeah, it depends. It hardly depends on a design of domain-specific language and on a design of the transformation of a program in this language into a sequence of tokens. So, for example, as I will describe it, when I will describe the neural VQA model, there will be a language where all input and output signatures are the same for all possible tokens for all possible operators. That's why we have we have a list structure of a sequential structure of a program, not a tree-like. And the main possible thing when we could have an exception is a type mismatch. So one of the things we want to deal with when we design a domain-specific language is to make this as more robust to these mismatches as we can. Okay. So for conclusion of this part of the speech, we showed that adding some structural knowledge in our algorithm could provide us benefits in quality, and applying neural networks for solving program learning and especially programming by examples types of tasks could result in a more robust algorithm for noisy data. So moving to the second part, we'll observe program learning module as a building block of a neural architecture. This will be in application for visual question answering systems, visual question answering problem. And the motivation behind it is that visual question answering is a field where there are a lot of concepts, both visual and semantic. People deal with these types of concepts pretty well. People deal with these types of concepts pretty well, and there is a lot of structure in this type of tasks. That's why it can be we can hope for getting some new results while adding some structural parts to our neural algorithm. And firstly, I would like to introduce a clever dataset on which both models that I'll observe will evaluate on. It simply consists of an image, a synthetically generated image that has a background and that has some geometrical figures on it. They are namely cylinders, spheres, and cubes. They can be of two different sizes, small and large, of two different materials, and of 8 possible colors. So these images are, I will not go deep into details how they generate them, but the scheme of the procedure would look like that. Well, firstly, we sample some latent scene representation of the generated of the image we want to generate. It contains all the possible information about the geometric figures and their positions in the picture. So, for example, in this scene representation, we can have the categorical values for size and all of these categorical qualities of the objects, and about their positions in the image. And the motivation behind designing this dataset, as authors claimed, is that VQA systems tend to learn the biases of the data and to rely on them. And they, despite it is a synthetically generated dataset, they were trying to make this as unbiased as possible. And they did so by making all of the possible distributions as close to uniform distribution as possible. For example, the distribution of cubic objects, of their positions in the space, and so on and so on. Second part of this dataset is questions related to the generated images. And there are 90 so-called question families in this dataset. And for each question family, we have one templated type of a program. And for any templated type of a program, we have some basic questions that has the same templates in it. So, for example, if we see a question, how many red things are there, it was generated by firstly sampling. It was generated by firstly sampling a picture, then sampling a question family corresponding to this type of program. It looks like we count the number, we count the objects that we get by filtering color C and filtering the material M. And in this time, color C corresponds to red and color M corresponds to nil, so they could not actually be represented in the question. Yeah, and at the right picture, the domain-specific language of Clever is presented, and it is very simple, and it mostly consists of filtering operators, Boolean operators, and counting operators. Because what we want because we want to extract the like this types of information from our image, and this is motivated by the types of questions that we generate. So going into the neural symbolic VQA model, so here is the large picture of representing the structure of the model, but it is not actually so difficult to understand. It contains three main modules. First module is so-called image parser that extracts information about objects. The objects that image contains, and translates it into a structural scene representation, which is shown by the picture, by the table at the right. So the second part is, we have a pair of image in question. So first thing to do is to process an image to get a structural scene representation. The second thing to do is to process the question and to generate a program that will solve the problem that this question states. And the next part will be in just applying this generated program to this generated structured scene representation to get an answer. Let's go to the details. So I made a little scheme from the at the right. So the first part is a scene parser, and it actually consists with the mask CNN for extracting segment proposals of all objects in the scene. Well, along with predicting the segmentation mask, it predicts also the categorical values, so the size, the shape, the color, and the material.
And what about the location?
And the location is the second part. So after extracting the segmentation mask with the categorical values, we have an additional convolutional neural network that we call a feature extraction network. And in this data set, this feature extracts only the positions. So the X, Y, and Z coordinates in our image. And what we do actually after we get our segmentation masks, we put it as an input of this convolutional neural network with the along with the original image resized for the convenient input shape. So, for example, in our model, the feature extractor network is ResNet34. So we need to resize an image and to put an image paired with a segment of an object into ResNet34 for predicting the predicting the position. As for the second part, we have a question parser that is generally an attention-based sequence-to-sequence model, where encoder is a bidirectional LSTM and the decoder is an LSTM. We have, as for details, we have two hidden layers with a hidden dimension of 256, and encoder and decoder activation have the similar have the same dimension. So it's just it's just a classical way to solve this sequence-to-sequence type of problem. The next part is our program executor that takes a generated program and evaluates it on a generated structural scene representation. So the designed domain-specific language consists of functional Python modules that are in one-to-one correspondence actually with the ones designed for a clever data set for the generation process. As I said while answering one of the questions, is that it was carefully designed that way that all the programs have the sequential structure. So all the operators have the same all the programs have the same input-output signatures. That's why we can just like sort them for any different for any different way. The only possible errors that may occur is a type mismatch. So it is a really convenient type of generating. It is a really convenient way for generating a program because the nature of our program of our question parser is autoregressive because we are solving the sequence-to-sequence task.
Could you provide an example of this Python code, this sequential Python code? Just to see how it looks like.
Well,
It was on one of the previous slides.
I believe here we can see. These are the functions for our domain-specific language in generating clever instances. But since all the operators are in one-to-one correspondence with the Python modules that authors of NSVQA present, that is very similar.
So no loops.
So we do not have loops. Yes, we just have a few number of we have a few number of possible types of operators and it's all about Boolean operators, counting operators, and filtering operators. That I believe at the very end of the presentation, after after thanks for attention, I have a slide with related to the second paper, but also that could show a possible implementation of this, but in a little bit another way.
But how do we preserve the consistency of the code? So we just output some sequence. Why this is, well, the true program?
Consistency in what sense? So
our output is just a set of well, symbols from the corresponding alphabet. Yes.
Yeah.
Like comma, some particular operator, and so on. Some sequence. Why this would be the correct program?
Okay. I didn't say about the training procedure because yeah, I'll move it to this. Yeah. So talking about the training procedure, we do not in this case, because this clever dataset is synthetically generated, there are annotations for all the possible things we could have. So there are annotations for programs. So we have an input example of an image paired with a question, and the question, as we know, is generated from a program. And we actually, in this dataset, we have a possibility to sample image paired with question, and also with the ground truth program. So we just like maximizing the likelihood.
And why the question is generated by the program? I thought that the program generates. I mean, the program defines the answer to the question.
Yeah. It is so. What we actually do is, in a clever dataset, we sample a program, and after sampling a program, we sample a question that corresponds to this problem.
And how,
program.
How can we find the corresponding question which corresponds to the given program?
It is like wired into the procedure of sampling. So we have 90 different families of questions, and in each family there is one program, one templated type of program, and it corresponds to 4 or 5, as if I'm not mistaken, types of questions.
So to understand that actually you're doing quite the opposite.
Yeah.
You first generate the question, then you can easily generate the program which corresponds to the given question according to some templates.
Yeah.
Right? And so, and this is the way how you can obtain, well, the training sample.
Yeah. So basically, I'd like to talk. I wanted to talk about it a little bit later, but yes, generally the authors of this model do the opposite thing to generating a clever sample. So I believe the aim is to see that providing the algorithm with structural knowledge about the data could improve its performance and could reduce its dependence on the amount of data. And this is what we will actually get, and this is what authors did. Because while generating a sample, we first generate a program, and after that we generate a question. There we have a question as an input, and we generate a program. So the opposite, we have the opposite direction of solving the problem. And while generating an image, we have a latent structure scene representation. And what we do is we recover this scene representation while executing and training our neural network.
Do you understand that this is actually a toy program? So in some sense, we know how to generate the exact program,
yeah,
which is defined by the given question.
Yeah, in some sense, this is right, and this is like an introductory part in this sense, because the second model will deal with these problems. Mm-hmm.
So your LSTM network generates a program in this like Python language, yes?
Yeah.
And the authors propose to maximize the likelihood.
Yeah.
Isn't it strange that you can generate the programs with quite a high likelihood, which are not correct programs? they will just not run.
And I didn't quite understand.
You can construct incorrect program from the functions you presented previously, which will have quite a high likelihood.
I believe they will not have a high likelihood because during training, our ground truth programs are the ones that we want to execute without exceptions and without errors occurred.
So if the program raises the exception, then
yeah, so while evaluating, we just consider this type of case. Okay, I understood the question. Is it about training or evaluation procedure?
probably training.
Probably training. Yeah. What do we typically have? So the gradient signals for our scene parser and question parser, the start point of these gradient signals is not the answer. This is the either program that we generated from our domain specific from the Clever data set, either as scene representation. So during training, we do not actually execute our programs. So while training, we have a scene parser, and it gets a gradient update by the scene ground truth. And we have a question parser that gets the gradient updates by program's ground truth.
So we do not have an end-to-end procedure. We train it by parts.
Sorry?
We train it by parts. So we have.
Yeah, we train by parts, but okay. While typing this scheme, I understood that there is actually. So I'll go then for a training procedure. So I believe if the question was about the question parser. I forgot to say that, yes, there is actually a second stage with reinforced gradient estimation, and I don't quite remember that authors put it in the paper anything about solving this problem of the okay, I remembered. So if while evaluating reinforced stage of learning, we do actually get the rewards from generating a program and from comparing it to an output. But when the error occurs, we just set the reward to 0. And we just ignore this gradient update. And in the evaluation stage, we just, if the error occurs, we just say that we were mistaken, we have a mistake in this in this instance, and okay, don't count. We count this example, but with 0 accuracy, something like this.
What is fine here is a program.
Yeah, it is a program.
It's the parameter of program generator.
So yeah, going from this question to to describing the training procedure, the first stage is supervised pre-training on question program pairs. And what is really interesting about it that it actually does not require a lot of programs. So we have 90 types of 90 families of programs, and giving three examples of questions from every family of a program is sufficient for achieving high results. And as for reinforce, yeah, we just maximize the probability of.
What do you mean by telling that we have 19 different types of programs?
Program families, as I described in the Clever dataset.
So actually, the operations, the operators. 19 different types of operators.
So we have 90 different types of program templates, So the programs about the shapes, the programs about the relationships between objects. So like the classification of types of questions.
Okay.
And since we have a program for each of the 90 different families of questions, while training on the supervised part of our procedure, so we like generate just 270 ground truth program strings, three ones from each question family. The second stage of training is applying reinforce. So theta is scene parser parameters, and phi is question parser parameters. And in this scenario, we maximize the probability of our program conditioned on a question of giving a correct answer, where image denoted by I, question denoted by Q, and answer denoted by A are generated just by taking them from the empirical distribution of the data set.
Fourth year students, do you understand why reinforce is used instead of implementation technique? Because the program is something discrete.
Yes, actually. And in here, we use reinforce, but there are a little bit of different techniques of reducing its variance. So we use a constant baseline, we use early stopping, and weight decay. Authors claim that it somehow that it reduces the variance of the estimator, and the training goes better. And going. Okay.
Speaking about the scene parser, so you train the scene parser itself in parts, am I right?
Yeah, I'll go back then because I started from the from the different sequence. So training in scene parser requires. So firstly, what do we get as training data? We use 4,000 clever images with annotations, and by annotation I mean the segmentation masks of objects, their categorical values. So the whole scene representation is used as an annotation for each image. So we pre-train mask RCNN with 30,000 of iterations on on the segmentation masks along with the categorical values. After that, we use a pre-trained mask RCNN, and we train the feature extraction CNN with a mean squared error loss, because we have ground truth values of our X, Y, and Z coordinates in the image. So it's like the whole process of learning is in parallel. So we firstly we could train it. Firstly, we should train scene parser, and then we train our question parser, and do not update weights of the scene parser.
You will not update the scene parser never?
Yes, because as you see, so in this functional, as I remember, authors do not update the weights during the reinforced stage, for example. So here they just minimize maximize the likelihood, and here they just generate an input, process it with a scene parser, generate a program, and update the program's way, the program generator's ways.
The last question about the RCNN. Why they use this quite an old network instead of let's say UNet or something like that?
Mask RCNN, that's 2018. They use mask RCNN.
Mask, yeah.
That's 2018.
And the paper neural symbolic. I'm sorry. And the paper neural symbolic VQA is from 18th year as well. So that's all about.
Because here data is synthetic. vision part is very simple. So like it's 100% accuracy because of synthetic data. Vision is
yeah, it's something like this, and that's why while having 70,000 of images in a Clever dataset, we can use just 4,000 because of this simplicity of data. So going into results, we have a near perfect quality of our NSVK system trained on 4,000 Clever images and on 270 programs. So these works are these works use different approaches, but most of them are in convolutional-based features or attentional-based processing of an image. And some of them, one of the most interesting is IEP, that was introduced by the authors of Clever dataset, is a benchmark for visual question answering modules on this dataset. And it also uses a program learning module, but it doesn't use the scene representation annotations. At the right, we see we have a comparison of our NSVQA versus IEP. This is the same baseline that I described before it. So we have a near perfect accuracy on the validation data set, and we have a promising accuracy that beats the baseline, even using a small amount of ground truth programs, while evaluating on the Clever Humans data set, where the questions do not have such a fixed structure, and we achieve comparable results with the previous algorithms.
And what is Clever Humans? Does it mean that the questions are formulated by humans?
Yeah. So the question.
Any restrictions?
I guess
with restrictions, but still.
But that's interesting. Which restrictions they used?
Unfortunately, I do not remember what type of restrictions there are, but authors claim that these types of questions do not have such a restricted, such a formal way of generating a question.
Well, hopefully so.
Yeah, so it is. It can be used as a benchmark for generalization on new types of instances.
Okay, question here.
Yeah.
Have they tried generalizing from one subset of synthetic programs to another subset of synthetic programs?
Yeah, they tried so, and I didn't add this table to the presentation, but there was the following thing. They split the dataset into two parts. They obviously get the near perfect results on the while training on the first subset, and training on the second subset, they get not so good results. But they claimed that it is because our feature extraction is bases hardly on the color of an image. That's why they did some different experiments.
But did they specifically split between like program templates? So like half of the program templates in the first half? Because like that's the critical thing about generalization in the grammar and in the actual program.
I do not remember whether they split it just by the program families, but they split it with the restrictions. So, for example, in the first subset, we have only cubes with 2 or 3 possible types of colors. In the second, so not only cubes, but a small subset of shapes, a small subset of colors, and in the second dataset, all the other things.
In the sense that you mean like there was never a red cube in the training set, but there is a red cube in the test set.
So something like that.
But both red and cube were in the training set. It's not like there is a totally new color which we have no idea what it is.
I don't remember fully the details fully, but there was such type of an experiment, and they tried to do something like making the pictures grayscale, and this turned out to lead to better generalization or something like that. So as for conclusion, we have a near perfect performance on Clever dataset, and we have a few number of ground truth programs and a few number of images during training. But we heavily rely on the ground truth scene decomposition. And we also rely on the ground truth programs, and that is the problem that we aim to solve. And it was actually solved using an elegant idea in the next module that we'll observe now. So the next module is called Neurosymbolic Concept Learner, and its basics. I just took the scheme on NSVQA and put in red the things that are different in our new model. So we in the previous model we have an explicit scene representation that we do not usually have in a real-world dataset, and we rely on the we heavily rely on it, and we also rely on the ground truth programs, which we do not usually have in the real-world tasks as the scene representations. So there are two bottlenecks which we aim to deal with. Well, okay.
What is the second bottleneck?
So the first is a scene representation, and the second is program execution. In terms of that, we aim to not use any ground truth programs. So we want to learn it a little bit of a different way, but okay, we can actually use reinforce or something like this while training question parser, which remains nearly the same. But there is another problem occurring. So as I type there, while training an SVQA, we had two mostly separate procedures about training scene parser on scene ground truth and about training question parser on programs ground truth, and then fine-tuning the question parser on with reinforce. And so here, what we actually get if we remove just the scene representation, we have no gradient signal for the image parser, we will make something similar to a scene parser, but it will it's something similar to scene structure, but we will make it in in a way that for each object we will make an embedding in some latent space of our neural net. But there is okay. But if we try to generate this type of a scene, we continue. So we didn't solve the problem of propagating the gradients into our image parser because there is no ground truth scene. Yes. So the approach that authors used is to propagate the gradients right through beginning from the answer. So in this time we face another problem. While propagating gradients from the answer, we need a differentiable program executor. While it is a discrete object which cannot be used, which cannot be differentiated in the previous. In the previous model. So the elegant idea proposed by authors is to use learnable, differentiable executor that will approximate the program execution made in the previous model, something like that. And so I'll go back into the motivation. In this model, we do not actually have ground truth scene representations, and we do not actually have ground truth programs. So the main thing, the main knowledge about the data that we provide the algorithm with is the domain-specific language, but we do not provide it with ground truth programs. So
but we know ground truth answers, right, to the questions.
What? Sorry, I didn't quite hear.
I told that we know ground truth answers to the questions. Otherwise, we couldn't propagate.
Yeah, of course. Yeah, so The answer for the question of how to propagate gradients is represented in this scheme. So basically what we have the same image parser, here denoted by theta v, v for visual. And we have a question and the semantic parser or question parser denoted by theta s, s for semantic. Then we have a visual representation. So we have this, so we have the scene, the scene table, but in this time it's a set of vectors, vector embeddings corresponding for all of the objects. Yes, then so we have a program and we have a set of embeddings of objects, and we just evaluate our program, our differentiable program executor on this on the scene representation in like a latent space. But authors called it a quasi-symbolic executor, and let's talk a little bit about its properties. So the two main definitions in the neural symbolic concept learner is a concept and an attribute. So every object, so we have different object attributes. It's like their qualities. For example, it can be red, it can be cubic, it can be whatever it is. And red, cubic are examples of concepts. And the attributes, its shape, its color, and etc.
But cubic, this is the characteristic of the shape. It should be concept.
Yeah, this is a concept. Maybe I told it not correctly, but this is a concept, and this is an element of the attribute set of shape. And in our neurosymbolic concept learner, what we do is that for all concepts, so like they are constant, we have learnable vector representations. And for all object attributes designed as functions in our domain-specific language, so for example, the function that, like in this picture, extracts the shape of the shape of the object, is a differentiable neural operator. So, and we can actually compare them in latent space. So, if we want to know that, if you want to somehow know whether our object in the scene is cube, we just put this embedding vector of an object into a neural operator that extracts its shape, and then measure the similarity of its shape with a constant shape of a cube that we also learn while the process.
Wait a minute, I still do not understand one thing. If concepts are related to the shapes, then why shape of is an attribute?
So it's like attribute is the
non-cubic form. It's nonsense, right? Cubes are always cubic.
I didn't understand. So the attributes, yeah. Well, this example I understand, of course, but so attributes are the names of qualities, and the concepts are examples of these qualities. So attributes are, for example, shape, color, and something like this. Concepts are cube, red, and something like this.
But you relate concepts to the shape already. Cube, cylinder, sphere.
Of course, you look at the scene and like detected some bounding box. You don't understand what is it. You need to like some operator on like this bounding box.
So we have
what is the shape of, what is the type of.
Yeah, thinking as a new. We have our program generated that, as in the previous model, was like just executed on the structural scene representation. While now we don't have scene representation in terms of just some categorical values and continuous values. We have this representation presented as embedding vectors.
Oh, okay, so each object is represented as a vector embedding.
As a vector embedding, yeah.
Whole concept, right? So you relate concept with the object, not with the object of particular shape, not with the cube, with the cylinder. But with the object 1, object 2, object 3 on the scene.
So while I believe this could be, I believe we could demonstrate it on during the evaluation we have an operator filter and we want to filter all cubes, cubic objects in our data set. Okay, yeah. And
then you apply
then we apply a binary operator that extracts the probability of an object being a cube, actually. And for doing so, what we do in this procedure is we like take the vector embedding of an object.
of each object on the scene.
Yeah, no, of each object of the scene, we process them with this neural operator that extracts this shape. Yes, shape of, like in this picture. And then we measure the cosine distance between the constant learnable vector called cube and the vector that we obtained after propagating our object through the neural operator shape of.
How do you tell the model what's cube and what's a cylinder? Like, why there are two? Like, where is the symmetry broken? Because one can think that there are two shapes, and then like which one is cube? Like, you have to tell the model somehow. The model should know like which one is cube.
So it should know the relationship between the concept and an attribute. Do you mean so, or something different?
I don't understand.
Imagine you have a child and you tell your child that all the cubes are called spheres, and the child can operate in the real world believing that cubes are named spheres. So without showing that this is in fact called a cube, it can believe that this is a
Okay, I understood, but
this notion has to be introduced somewhere, like in the model. How do you know the vector?
so yeah, I'll go further into details and I'll tell about. So about the question of concepts, these notions, I believe these notions arise where we make a semantic parsing of our question, and after parsing it into a program and executing it, we have like a token that corresponds to a filter or something like that. Or maybe I didn't understand it well, but
It seems to be a classification problem.
yeah, it's
To learn a classifier, you need to know to get the classes somehow, and the claim is that there is no classes.
so maybe I will explain it if I go further. So in this particular example, we, as I said, we propagate the object through the neural operator. We measure its cosine distance with the learnable vector of cube, and then perform and then output the probability with the sigmoid function with the gamma and t parameters of shift and scale.
So red and cube are the concepts. Color,
Yeah.
shape,
Are attributes, yes.
Now it's more or less clear. So we can learn the vector representation for the concepts. The only question which remained open, as far as I understood, was how we assign what particular concept corresponding to what particular vector representation. So how do we assign that this vector representation corresponds to red?
I just wired into the model. So we have not as much of concepts, and
All
so
concepts are predefined.
yeah, so they are predefined and so yeah, they are initialized randomly, but we know that this vector is the vector of cube, and this is a vector of something different, something like that.
So I think this was an answer to the question.
Mm-hmm.
I still don't quite get. So like if we have input examples and output examples and domain-specific language, that's all we have, right? When we train the model.
Mm-hmm. So and we have ground truth segmentation masks also for for image parser.
With that, how do we match the words in domain-specific language to their meanings?
It will be should be the next step.
Yeah, it will be in one of the last slides about the model, about training, and something like, I believe it will answer your question. So as defined in previous model, we use a pre-trained mask CNN. So pre-trained means that we extract 4,000 of clever images and train on ground truth segmentation masks. So mask CNN is used for extracting object proposals. Then we take the original image. We get so-called region-based features by the row line operations, and the image-based features get from the convolutional neural net, and they are concatenated, presenting the vector embedding of an object. So by adding image level features, we add some contextual information to the embedding of the object. So, and for domain-specific language and question parser, we have a DSL very similar to the one in NSVQA. So the differences are insufficient to talk about it. And as for the question parser, we have bidirectional GRU and the GRU decoder. Bidirectional GRU encoder and GRU decoder. So going back to the quasi-symbolic properties and to the executor, all the operations are made probabilistic for the differentiability. So, for example, if we want to filter a set of objects into another set of objects, we do not just output the new subset, but we output the probabilities that for every object, we output a probability that we relate to this object and we want it to be in the next part of execution of our neurosymbolic executor. And it is denoted by so-called masks, and while performing these operations, our inputs are a pair of current scene and the mask get from the previous operator. And as for training, we get the follows. So we have the weights of the visual scene parser, theta v, and the weights of the semantic parser, theta s. And it is important to mention that our executor, so we need an answer to be output, and our executor actually is actually presented as a multi-class classifier. So we have not so the possible answers are yes, no, shapes, colors, size, material, and so on, and some fixed number of integer possible outputs. So bounded by some constant. Bounded by some constant. So we train. Actually, we train a classifier. And the functional is that, is the expectation taken over programs, as in the previous case, but we maximize not the indicator, but the probability, because our executor outputs the vector of probabilities, and we have the ground truth answer that corresponds to a binary vector with one unit, and other values are 0. So for the visual scene parser, we minimize the cross entropy between answer and execution result. So by minimizing by cross entropy, I mean because we have an execution we have an expectation over over programs, and by cross entropy, I mean that we if I'm not mistaken, I mean that we sample we sample some programs from our question parser, and we compute the mean cross entropy between these particular samples of programs.
Could you please repeat how the executor is trained or defined? Probably I missed something.
What?
The executor, how is it trained or how is it defined?
So the executor is just so yeah, we have So it takes the program as an input, so the sequence of tokens, and the perception, so it's like the scene of our embedded vectors. And the executor takes the program and makes the evaluation in this style that presented in the right picture. So everything is made differentiable, even the mapping of a token into a neural attribute or something like this.
I think you can think of every operation, like every operation of the language converted into a neural network layer with some parameters and some input-outputs, and then the structure is fixed. And then you just building blocks, you're combining building blocks. So if you have this neural program, you know how to execute it, just run it.
Yes.
It's like a feedforward pass.
But the weights of these neural blocks, are they trainable?
So yeah, of course. Embeddings for concepts are trainable, and attributes networks are trainable also.
But these are not attributes. These are operators, right? For each operator, you have trainable neural network?
No, it's...
There are two pieces. One is supervised loss, one is reinforced. So the order of operators is done with reinforced, but the rest is supervised.
Yeah, I believe it's a bit about different thing. So, for example, a filter operator is presented, I have a slide at the end. The filter operator is presented as a differentiable smooth version of the filter operation as it was in a program executor in the previous model. So we have like a list of functions that are deterministic and not trainable. That use attributes and concepts as their inputs, and this scene, of course. So yeah, it's just a set of differentiable operations that are designed as, for example, by...
These are just smooth versions of some deterministic...
Yeah. For example, instead of taking an argmax, we can use softmax, and it's like something in the same way.
Okay.
So yeah, the term for the visual scene parser is the minimization of cross entropy between between our answer and the result of our execution. And as for semantic parser, we use reinforce with some variance reduction techniques to train it just by sampling image question and answer from the dataset, and after that sampling a program from our distribution of the model. We also use so-called curriculum learning, which authors were motivated by the way humans learn. So, for example, we actually start with some very simple scenes and very simple questions about the object-based questions. The second part will be in training on questions about the relationship between objects. The third part will be in training on simple scenes but quite difficult questions, and at the very end we will train on arbitrary questions and arbitrary scenes. So because we have no annotations on programs and because we have no annotation on programs, it could be seen as a thing that helps to train using a reinforce, for example, for question parsing, question parsing type of loss.
Excuse me, am I right that understand correctly that to start learning the reinforce, you have to guess the correct program randomly, and if you have simple questions, it's easier to guess.
Yes, it's something like this. So if we consider the functional of the previous model where we have an indicator, so starting learning just with reinforce will not converge never, because we have just two possible answers, two possible rewards, 1 and 0, and 1 we get if we sample the program that would guess the output correctly. And in this way, we use some off-policy search techniques, and we use this curriculum learning, I believe, for training the question parser in a non-supervised by programs way. Something like that. So for training, we have 5,000 of clever images and 20 questions generated for each image during the whole process of learning. And we use just in the like in the previous model, Maskar CNN pre-trained on 4,000 images on on segmentation mask annotations. And as for results, we can see these our models compares with different models that use program annotations and with models that do not use it. So an overall accuracy is 98.9%, and it is comparable with one of the most comparable with one of the models that also do not use the do not use the annotated programs. But this was done in I need to remember it. It was done learning just on a subset of images on 5,000. So if we train this type of model on the whole set of images from Clever, we get an accuracy of 99.2%, which outperforms all the previous models that do not use that do not use the program annotations, and even outperform the models that do use such type of annotations. This is shown in data efficiency table. So accuracy on 10% of data is what was presented in the previous slide, where we trained on 5,000 of images, and 99.2 is when we train on the whole set of Clever images. And as for the right, combinatorial generalization is all about splitting the data set into 4 parts and making the learning process only on the one part. And they are split actually. And as I remember, they are split in the way that 4 of these splits correspond to 4 stages of training procedure. So simple questions and simple scenes, simple scenes and relationship questions, simple scenes and difficult questions, and difficult scenes and difficult questions. And we try to learn only on simple ones to predict the more complicated. And we actually get really promising results in this evaluation. So, as a conclusion, this structural in this model we have a structural program learning part as a combined with a differentiable executor. We achieve a near perfect accuracy on Clever visual question answering dataset and problem. We do not use the ground truth programs, and we do not use ground truth scene representations. So we use just an answer and the segmentation mask for mask CNN pre-training. That's all we use, and that's what we get.
Curriculum learning.
Okay.
I think it's pretty important because you have to show very simple questions first, and it's hard to reorganize your data.
Someone creates this curriculum.
Yeah.
Okay. Yes, I understood. Yes, it's also a structure. Can be seen as a structural part of the data, but it is not so heavily introduced as in the previous model.
Can I ask a question?
Of course.
There is a whole line of work from Berkeley with the QoS neural model networks, which seems very similar. So there is like the first paper was doing stuff with program annotations, then they were using reinforce on the same model, then they got rid of reinforce, and they were like improving accuracy all the way. It seems like very similar. Can you comment on the relations to that? Does this paper mention?
But I guess they were present in the table. No? NMN?
No, NMN, I haven't seen that. So NMN also compares to Mach, so they beat Mach like crazy. They said Mach all the bad math.
So yeah, here there is an NMN in the very beginning.
They give NMN program annotations because there is NMN without program annotations.
Okay, well, maybe they didn't know about it, or maybe they didn't want to compare with it, or maybe there wasn't these models weren't introduced in when this paper was published. So maybe.
Any more questions?
So that's all, and
Okay,
thanks for your attention.
Let us thank the speaker for very interesting talk.